The third free response question on the E&M practice test is a Faraday's law problem, but it also has a little bit of circuit stuff thrown in, and that's very common when you're looking at induced EMFs to have to go through and you find voltage, and then you're also going to go through and you're going to figure out what the current is or power, those different things. So we have a square conducting loop of side L. We have two identical light bulbs, 1 and 2. There's a magnetic field that's into the page, and the magnetic field is increasing at the rate that's given, AT plus B, where A and B are positive constants. The light bulbs each have constant resistance R0. Express all answers in terms of the given quantities and fundamental constants. So this one you're not going to do anything numerically. You're going to go through and you're going to solve everything algebraically. Again, this actually in some ways makes it easier because there's not a bunch of things that you have to keep plugging into your calculator, but you have to go through and you have to work with the algebra. So first, derive an expression for the magnitude of the EMF generated in the loop. So again, it's asking for the magnitude of the EMF. So the magnitude of the EMF is the magnitude of the derivative of the magnetic flux with respect to time. Again, magnetic flux is magnetic field times area. So this is a square loop, so it's an easy area to calculate. Its area is L times L, so it's L squared. And the magnetic field as a function of time, they give us. So this is going to be the absolute value of the derivative with respect to time of the quantity AT plus B times the quantity capital L squared. The L squared is a constant. So I just pull it up front. And I take the derivative of AT plus B. The derivative of AT is just A. The derivative of B is 0. And so this is my answer. The EMF generated in the loop is A times L squared. Again, this is a straightforward example. You need to know what to do with the magnetic field, but they give you a magnetic field equation. You need to do magnetic field times the area, and then you have to take the derivative of it. Sometimes it's much more complicated. You have a magnetic field that's not constant, and so you're going to have to go through and break this up into strips and integrate to get your flux. This is a little bit simpler version. So part A should have been a fairly simple part. Again, if you understand induced EMF, again, this is definitely the things talked about at the end of the year, so you have to make sure that you're learning this. If you're going through and doing the homework and looking at this, you need to make sure that you understand these key ideas. There's definitely going to be induced EMF on the AP test. Maybe it's just going to be all in the multiple choice section, but a lot of times this does come up in the free response section. Part B, determine an expression for the current through bulb 2. Well, some people just said that the current equals the voltage over the resistance. And that was not enough to get credit because you need to say what your voltage is, you need to say what your resistance is. You need to at least calculate what the resistance of your circuit is. There, you've got two light bulbs. Those two light bulbs are connected together in series. The current is flowing around that loop. And so the resistance is 2 times R0. And even if you just recognize that, if you had no idea how to calculate the EMF generated in the loop, even if you could recognize that, that could possibly get you some credit. For this one, it would have, but sometimes that'll give you credit. So at least try and plug in the values that you're given. And if you didn't know how to do part A, then say the voltage should be your answer to part A. Again, you should know that an EMF that's generated is a voltage. But this would be L squared times A. And that would be the answer. Indicate on the diagram above the direction of the current through bulb 2. So looking back at this, we have a magnetic field that's into the page. And that magnetic field is increasing. If I look at what the magnetic field does as a function of time, as t gets bigger, that magnetic field gets bigger. So if the magnetic field is into the page and increasing, then that means that the magnetic flux is increasing into the page. That means that the induced magnetic field, which is the magnetic field due to the induced current, tries to oppose that increase. So the way that it can oppose that increase in flux is to have a magnetic field that's pointing in the opposite direction to cancel it out, to bring it back down to its lower original value. If the induced magnetic field is out of the page, and then you want to use that to figure out what direction the current is flowing, remember, if you take your right hand, if the thumb of your right hand points in the direction that the current is flowing, your fingers wrap around in the direction of the magnetic field. So if I'm looking at this right segment, so if I'm looking at the current through 2, I need my fingers, when they're to the left of light bulb 2, to be pointing out of the page. So I need the magnetic field at the center of that square, due to this current around it, to be pointing out of the page. And the only way that I can do that is if my thumb is pointing up. And so that means that this current is going to have to be flowing upwards. So this current is going around counterclockwise. That counterclockwise current causes a magnetic field that's out of the board. And that magnetic field out of the board is created to try and keep the flux constant. The magnetic field is into the page and it's getting bigger, so that's increasing the flux. So there's this magnetic field that's created to try and cancel that out. Again, you need to understand how to think through these problems. It definitely takes some practice. This is something that a lot of students struggle with. Again, in the research that I did in graduate school, this was definitely something that a lot of people had trouble with. We wrote a whole paper specifically on student misunderstandings of Lenz's law and induced voltages and currents. And so this is something that really takes some practice. Definitely you can come and talk to me, you can see me, and we can go over different situations, because it's very easy to give you different situations of the area of the loop changing, because so the loop is expanding, or the loop is contracting, or the loop is rotating, or the magnetic field is increasing, and the magnetic field is decreasing, and ask you about the direction of the induced magnetic field or the direction of the induced current in each of those different cases. That may be something that may be useful, and if that is, then talk to me outside of class, talk to me at a review session, talk to me before or after school, and we can go through and we can look at all of those to make sure that you really understand them inside and out. Okay, derive an expression for the power dissipated in bulb 1. It's specifically looking for the power in just bulb 1. So power is either current times voltage, or power is the current squared times the resistance, or it's the voltage squared over the resistance. Either way. But again, writing those down is not enough. You needed to substitute in values. The current through bulb 2 is what we just calculated. The current through bulb 2 is the same as the current through bulb 1. But since this is asking for the power dissipated in just bulb 1, again, these two light bulbs are in series. It's weird to think of them as being in series because we don't see a battery. But this changing magnetic field is acting as if it was a battery that was inserted in that wire. And so the voltage across just bulb 1 is half of the induced voltage. So since it's the voltage across bulb 1 only, then we have half the voltage across bulb 1 and half of the voltage across bulb 2. And so you wouldn't need to simplify that, although if you did, you would have L to the fourth A squared over 4R0. But it was okay to leave it the way it was. Again, if I did current squared times resistance, this would be L squared A over 2R0 squared times R. And the resistance is the resistance of just bulb 1, so that's R0. And if I do that, L squared squared is L to the fourth, A squared is A squared. The denominator squared is 2R squared, so that's 2 squared R squared, so that's 4R squared. And then I'm multiplying by R0, so that just gives me the 4R. So either way, those would both be correct ways of doing it. But again, it was common to use the full voltage instead of the voltage across just bulb 1. Those three parts, again, those were fairly quick parts. Those three parts are the calculation parts. Now they get into some conceptual things, which can actually, these were pretty tricky, but if you really understand induced EMF and you really understand properties of circuits, then you can get them. So another identical bulb, bulb 3, is now connected in parallel with bulb 2, but is entirely outside the magnetic field as shown below. So one thing that's important is there's no flux through this part right here. Our only flux is still through that part that we were looking at before. And so this flux through this loop acts like there's a battery in that wire. And if you think of it that way, and maybe it helps for you to draw it that way, then you can easily see that you have current that's flowing here, and then some goes this way and some goes this way, and then they join back together. You have those bulbs in parallel, but those two parallel bulbs are in series with bulb 1. And if you think of it that way, again, I think that that's an extremely helpful way of doing it personally. But if you think of it that way, then it becomes clear what you have happening. You still have the same voltage that's being induced because you still have the same magnetic flux. You still have the same size magnetic flux. It's the same size loop, same rate of change of the magnetic field. And so if you have the same voltage that's induced in that circuit, if you have the same size battery that's placed in that circuit, you now have those two resistors that are in parallel with each other. So those two resistors in parallel with each other, they add up to give less resistance. And so if there's less resistance over on this side, then that means that there's less total resistance in the circuit. And so how does the brightness of bulb 1 compare to what it was in the previous circuit? It's going to be brighter. And the reason for that is putting bulb 3 in parallel with bulb 2 decreases the overall resistance of this circuit. And if the overall resistance is decreased, then the total current is going to increase. Bulb 1 has the full current flowing through it before it splits through 2 and 3. And so if there's more current flowing through bulb 1, it's going to be brighter. Again, you would need to not just mark brighter and skip on, and not just say brighter because less resistance. You would really need to explain why that's true. But again, I really think that for a lot of people, thinking about the fact that there's this battery, this EMF that's induced acts just like this battery, to see that you have these two splits of the current, that really makes it much easier to see, because then we're going to be able to see this for this next question. Except for the next question, it's like there's two batteries. So there'll be a few different ways of looking at this. So now the portion of the circuit containing bulb 3 is removed, and a wire is added to connect the midpoints of the top and bottom of the original loop. How does the brightness of bulb 1 compare to what it was in the first circuit? Well, one way of looking at this is that I have two loops. So I have this loop on this side. Expanding that makes it a little bit tough to see, but you have this loop on this side, and you have this loop on the other side. But they each have half the area that they had before. So it's like they each have a battery that was half as big. And we looked at a circuit like this where we had a battery that was connected to one light bulb, connected to another light bulb with another battery. We looked at this in the lab. And then we looked at what happened when we connected a wire between those two spots. And we saw that no current flowed through that wire. And it didn't change the brightness of the bulbs. And so when we did a circuit like this, we added the two batteries together to get the total voltage, and we added the two resistors together to get the total resistance. And so it acted like a single battery with a single light bulb. But again, this is each of these, if we're looking at this in terms of there's this voltage induced, so it's kind of like a battery, each of those is half of the voltage that we had before. And so putting those together, it gives us the full voltage that we had before with the same total resistance, and so we have the same current that's flowing. So that means that these bulbs are going to have the same brightness. The other way of explaining that is by saying that in this loop on this side, you have a current that's flowing. Well, actually, I drew it the wrong way. From what we said before, we said that on, if I'm looking at this loop on the left-hand side, then the current, due to that changing magnetic flux, based on our reasoning up here, the current on that left side was upwards. again, that's just looking at the idea that we have this changing magnetic flux. We needed to have my induced field is out of the board. So that means that in this wire, you need to have a current that's flowing up this way to produce that outward magnetic field. But if I look at the loop on the other half, if I need an outward pointing induced magnetic field, then that means that the current needs to be flowing down through this wire. Exactly the same size current. And so if we look at that, those two currents cancel each other out. Those two currents add up to 0. That wire has no current through it. That wire has no effect on the circuit. Again, when we saw that in the lab, that was counterintuitive for people in this situation here. But if you truly ended up understanding why that was true after that lab, then you understand why this is true. And there were several people, as I was grading this, that got this correct, that they figured out that you have these currents flowing in opposite directions, and so things are going to be the same. So there were some people who got full credit for this question. So D and E were really very conceptual types of questions. So if I go through and I look at the scoring guidelines, part A of the question was asking for the magnitude of the induced EMF. And so the magnitude of the induced EMF is the absolute value of the rate of change of the magnetic flux. So it was 1 point for recognizing that the area was constant in time. So you just had to do the area times the derivative of the magnetic field with respect to time. If you just wrote that down, that was okay. If you just said that E equaled d phi dt, the derivative of flux with respect to time, that was not enough. If you wrote that E equals the derivative of AB with respect to time, that would not be enough. You needed to show that you understood that the derivative of the magnetic field times the area was just the area times the derivative of the magnetic field. And then it was 1 point for actually correctly taking the derivative of the magnetic field. The derivative of that magnetic field, the derivative of AT minus or AT plus B, was just A. Again, it looks like a faint plus mark on the screen. It's definitely much brighter when I look at the computer, but on the projector it was fairly faint. And so it doesn't matter. The derivative of AT plus B is just A. And then it was 1 point for actually putting that together, that it was A times the area. And then it was 1 point, and so you needed to have that the area was L squared. And then it was 1 point for actually showing that you found the magnitude, so not making it a negative answer, but actually taking the absolute value and making it positive. So you do need to understand what they mean by magnitude. Part B, the resistors are in series, so the total current flows through both of them. So the current is the voltage over R total, but you had to calculate what that total resistance was. So it was 1 point for correctly answering that the total resistance was 2R0, and then it was 1 point for correctly substituting the value from part A. An alternate solution, the two resistors have equal resistance, so the EMF across each is half of the total EMF. So you take half of the total voltage divided by one of the resistors, that would give you those currents. And then for correctly simplifying. Now for this, it would not be enough to just say the current is the voltage over the resistance, because you need to say what voltage and what resistance. So you need to plug in those values. For the direction of the current, showing that the current flows upwards or counterclockwise around the loop. It was just 1 point. Part C, current times voltage, or current squared times resistance, or voltage squared times resistance. It was 1 point for substituting one correct value into one of the above expressions. So just writing them down was not enough. But if you said that it was, if you came up with some current in part B times the voltage, that would be okay. Again, it doesn't have to be a correct value as long as it's consistent with your answers to parts A and B. So if you don't know how to do that, but you realize that for this answer, you need your answer to A and you need your answer to B, somehow come up with an answer for those. Just write down an answer. Don't make it something simple like just 2, but you need to go through and come up with your best try at some type of an answer. And you need to show specifically that you're taking those things. And it would actually even be okay if you wrote this down and you said that this is the answer to B and this is your answer to A. From what I understand about how they grade that, even just saying that would be enough, because that shows that you know to plug in your answer to part B and your answer to part A into those spots. And so they would count that as correctly substituting, even if you didn't actually put anything in because you had no values there. They would let you get that point because even though you had no values, you knew what you would do with them. So just writing the equation down doesn't show that understanding, but saying you know what those values in that equation actually are does show that understanding. And so it was substituting one correct value into above expression was 1 point, and for substituting a second correct value in the chosen expression would be the other point. But what I said there of answer to B and answer to A, that would only get you one of the points. It would show that you know what to do, but that second point is really for going through, putting the second value in correctly and calculating it out. Again, you don't have to simplify, but you would need to have the correct answer actually for the second point. Or again, an answer that's consistent with your previous answers. So they just saying answer to B, answer to A, they would not give you the credit, I don't believe. But if you made up an answer to B and you made up an answer to A and you put those in correctly, even though your answer is wrong, they would give you the credit for it. For part D, the conceptual part, for indicating that bulb 1 was brighter, it was 1 point. Even if all you did was you just guessed, you got 1 point. For any indication that the EMF is the same as the original circuit, since there's no flux through the added loop, that was 1 point. For stating that the adding the bulb in parallel with bulb 2 decreases the overall resistance of the circuit, that was 1 point. And then saying that less overall resistance means the total current is bigger, which is the current through bulb 1, that was the final point. Again, if you go back and you listen to the explanation that I gave, those were all pieces that I described. And so you need to talk about that you have the same voltage there, but those bulbs 2 and 3 are in parallel with each other, so you decrease the resistance. Decreasing the resistance increases the current, and the current is what flows through, the total current is what flows through bulb 1, so bulb 1 will be brighter. Finally, part E was worth 2 points. So D, there was a lot more explanation, so it was worth more points. You wouldn't have known that heading in, but because there was more explanation involved, they gave more points for that. Part E was 2 points. 1 point for indicating the bulb was the same brightness, and 1 point for a correct justification. So again, you had a 1 out of 3 guess, brighter, same, or dimmer. You had a 1 out of 3 guess to get that first point, and then you had to justify it. Again, a lot of times they won't give you that credit unless there's a correct justification or a partially correct justification to go with it. For this one, they did. So the correct justification, since each loop has half the area, each has half the original EMF, but also has half the resistance, so the current and the power is the same. Where the two loops are essentially identical, the flux through each loop would create an EMF that's counterclockwise. Since these EMFs are in opposite directions in the central wire, the net effect is that there's no EMF in that wire. Therefore, the situation is equivalent to the original one. We didn't say it in terms of the EMF is in opposite directions in the central wire. So that's the voltage change is opposite. We said it in terms of the current. And again, that's that electromotive force that's pushing on the current. So it really is saying the same thing, just slightly different. And so their comments on this. So this was assessing students' understanding of induced EMF and its effect in various circuits. And some parts of the problem also assessed mastery of simple circuits. So again, that's why there was some, the fact that there was some magnetism stuff in problem number 2. There was now some basic circuit stuff in question number 3. So the two together gave almost a full magnetism question and a full circuit question. The average score was 6.39 out of 15. About 18% earned scores of 12 or higher, and about 33% earned scores of 3 or below. Again, it was not uncommon for them to have, 1 or 2 points, or for people to leave it completely blank. Again, a lot of people think that the Faraday's law problems are, the most difficult, and at first, conceptually, they are. But if you look at what we had to do, just in terms of the work that you had to do, the amount of work that you had to do, it was much less for this problem, but it was a lot more thinking, and it was a lot more conceptual. Common student errors or omissions. In part A, many students had difficulties calculating the derivative of the flux. They incorrectly manipulated the symbols associated with the derivative. In expressing the flux as the integral of B dA, many students incorrectly obtained an expression that was the integral of BT with respect to time. Not the correct thing. You're not integrating B with respect to time, you're integrating B with respect to area when you're looking at the flux. And if the magnetic field is constant over that area, then it's just B times the area. A common mistake in part C was to substitute current or voltage inconsistently. For example, using the voltage of the circuit as the voltage to calculate the power that was dissipated in only one resistor. Again, not recognizing that you had half the voltage across the light bulb. That was a big deal. In parts D and E, students had difficulties clearly distinguishing between the factors that determine the value of the EMF, the dependence on the magnetic field on the time, and the area through which the magnetic field was established, and the characteristics of the circuit in which the effect of the EMF is manifested. So again, what they're saying there in parts D and E, students had trouble understanding how induced EMF played a role in these circuits, and how putting the different light bulbs there, how that changed the resistance. So specifically the combination of resistors that they had. Based on your experience, what is something that people could do to increase their performance? You need to get more practice in calculating derivatives and integrals using physical quantities. So again, on your homework, that's one of the reasons that I gave you several problems that involved taking derivatives of expressions. There was one with a magnetic field that varied as E to some power, and so getting some different practice with some of those different ones. And then giving students more exposure to problems involving induced EMFs in situations that go beyond the simplest standard examples offered in most textbooks. So again, several of the problems that are on the homework are to try and push you past that. You really need to go through and understand that homework assignment in order to understand a lot of the types of problems that they could do. And if you really understand the homework problems inside and out, you should be able to do most of the EMF problems that they would do. One quick thing that I would like to point out in this, I had specifically said that this V1 was the answer to A, but it should have been the answer to A divided by 2. So they definitely wouldn't give you credit for that, saying that it was the answer to B and the answer to A divided by 2, they actually maybe would have given you 2 points for that, even if you didn't have any of those answers. Because it would show that you would understand what to do, and it's not just simply plugging it in, but there's a little bit of extra understanding there. And so it's possible that they would do that, but again, you would, the best way to do that, to make sure that they're going to give you credit, is to come up with some magnetic field. Even if you say, I don't think this is correct, but because I need it in a later part, I'm going to say that the EMF is blah, blah, blah. You plug something in. That lets them know that, it came out of thin air, but you realize that you need that answer for later parts and that you're going to use that correctly in those later parts. Again, I highly recommend that you go through and you look at Faraday's law problems. If you look at the problems that are in the binder, there's a few different Faraday's law problems that they ask in terms of free response questions. Again, the third free response question is not always a Faraday's law problem. Sometimes it's just a conductor moving through a magnetic field. And so that's the motional EMF idea, where that was VLB, the speed times the length of the rod times the magnetic field. That gave you the voltage between the two ends. Sometimes the third question is an Ampere's law problem. If there was not a Gauss's law problem in the first problem, there's often an Ampere's law problem on there. Not always, but that's kind of the way it works, is they're usually going to ask you one of those two things. For the first question, that often is electric fields and voltages and some other things, it's most often Gauss's law. Second most often is point charges. And third thing is the continuous charge distributions like a ring or a rod. The second question is almost always a circuit question, but it could be an induced EMF question, a simple induced EMF question where most of it deals with looking at resistances and looking at circuits. So sometimes questions 2 and 3 get mixed together where they're both part magnetism and part circuits. The third question, again, is most often a Faraday's law question, but sometimes it's an Ampere's law question. So again, if you're trying to make sure that you understand things, the first thing to do is to make sure that you understand Gauss's law, RC and LC circuit problems, just basic circuit problems with, some switches and some different parts of circuits, and Faraday's law problems. Those are going to be the things that you see most often. If you go through the binder, again, question 1, 2, 3, those all go together from different years. Then it goes on to the next year, questions 1, 2, 3. If you look at that, you'll see consistently that the most common thing is Gauss's law. The most common thing is some type of LC or RC circuit, or both. And the third thing is usually some type of Faraday's law problem. But there are a lot of different ways that they can do those problems. The best thing to do is to look through the binder. Even if you don't have time to solve all the problems in the binder, I mean, you definitely couldn't solve all of them, but even if you didn't have time to solve problems, there's a lot that could be done by just looking at them, thinking about what you would need to do. I definitely suggest trying to do some of them, but then once you've kind of reached a point where you've done several problems and you're trying to get more review and you want to get through several more problems without taking a full, the full amount of time to work it all the way out, definitely look through it and think through each part. At least think about, okay, what concept do I need to use? How would I set this up? What should I do? Look at the next part. Okay, oh yeah, this is going to involve my answer to part A. This is what I need to do. If you think through those steps, that really is the most important thing. if you can understand how to go from step to step and what concept to use on each step, that's going to be the key to the problems. And if you can figure that out for the majority of the steps, you can easily get 20 to 30 points on this free response section. 20 points out of the 45, again, that's a little bit under 7 points per question. That's an okay average for this. Um, you know, if you got 20 points on the one section and you got 20 points on the free response section also, that would get you into a decent range. Again, looking at the statistics that we had for our class, specifically I want to just look at what the cut scores were. But if you could get 20 points or so in the multiple choice section and 20 points or so in the free response section, so average about 7 out of 12, that would put you right here in this 4 range. Again, it might be a high 3, it might be a low 4. I mean, that's right in that range. 20 points in the multiple choice section is very doable. Again, I would say that, you know, these two are definitely above that, but these are right around that 20 points. You need to go back and look at your multiple choice test. But if you do that, that is going to help you out. That's going to help you understand that. I think a lot of people should have easily, should easily be able to gain 6 or 7 points in the multiple choice section. Get 6 or 7 more questions correct, or at least 5 or 6 more correct, which gains you, 45, 35ths, so that's going to gain you 6 or 7 points. And so if you could increase that score by 4 or 5 points easily, maybe 6 or 7. Again, depending on where you're at on that scale, you might have a lot more room to improve. And if you can increase your free response score, again, if you can get your average up to even just half, you can get yourself easily into that 3 range. But again, it seems like it should be easy to get into that range, but it just means if you don't, that means that you just haven't put everything together yet. It doesn't mean that you don't understand the individual topics, but it does mean that you had trouble putting some things together. So again, there are a lot of things that you can do for review, but with a good, solid review, which can be difficult when you're taking multiple AP tests, but if you're able to put in a good, solid review over the weekend, you should be able to be, more productive on the test, get more points, and hopefully be more successful. I think quite a few people who are taking the test could easily bump themselves up if they were on the low end of a score, get onto the high end of the score, which is an important thing because these cut scores often are, change. They might be a little bit higher than this. And so if you can get yourself up into the mid to high range of that score, then that means that you're pretty solid in that score. And that means that you might bump up to the next score. But again, it all depends on things. So if your total points are, around this 30 to 34 range, where that's right around the cutoff for getting a 3 or higher. Some years that's going to be okay, some years that's not. And so if you can get yourself, even just a handful more points, if you can get yourself, 5 or 6 more points, then that gets you solidly in this region, which is going to allow you to be a little bit more comfortable with your score. You're not leaving as much up to the graders in where you're going to fall. Again, it works that way for any of the scores. So you're trying to maximize your number of points. You're trying to go through and find as many ways that you can get a point here and a point there, because all those points add up. You know, go through, spend some time reviewing, come into the review session over the weekend if you're able to. If not, try and ask some questions. Just looking over the homework is not going to be the best way to do that. It's definitely a good thing to do, especially for the induced EMF. It might help you a little bit. But you definitely need to do problems out of the binder. Looking at homework problems is not a bad thing to do, but it just by itself, that probably won't be enough. Again, good luck with your studying, and with hard work, hopefully you will achieve the results you want.